You have probably been told, at some point, that scientists already know how the universe ends. It expands, it cools, the stars burn out one by one, and everything fades into an endless, freezing dark. It is one of those facts that feels finished, filed away, with nothing left to argue about. But here is what that tidy story quietly leaves out. The entire ending hangs on a single ingredient we cannot see, cannot explain, and have only just learned to measure. And in March of 2025, the largest map of the universe ever made looked back across 11 billion years and found that this ingredient may be changing. Dark energy, the invisible force driving everything apart, appears to be weakening. And if it is truly weakening, then the ending you were promised was settled was never really settled at all. Get comfortable and settle in. Hit subscribe if you're new here, because by the end of this, the phrase "how the universe ends" is going to feel far less certain and far more alive than it does right now. Now, let's slowly ease into this. Part 1. The map that should not have frightened anyone. Somewhere in the Arizona desert, a machine spent 3 years quietly drawing a map, and when the map was finished, it had done something no one had asked it to do. It had reopened the question of how the universe ends. The machine has a name that sounds like it belongs on the side of a filing cabinet. It is called the Dark Energy Spectroscopic Instrument, and the people who built it simply call it DESI. It rides on the back of a telescope that has been staring at the sky since before most of us were born, the Male 4-meter telescope, perched on a mountain called Kitt Peak, southwest of Tucson. From the outside, the telescope looks like nothing special. It looks like a white cylinder inside a dome, the kind of thing you have seen in 100 photographs of observatories. But at the top of that cylinder, where the starlight comes to a focus, there is something that almost feels alive. Let me put you inside the dome for a moment, because this is where the story really begins. It is night. The slit in the dome is open to a sky so dark and so crowded with stars that it does not look like the sky you know from a city. The air is thin and cold and completely still. And on the focal plane of the telescope, in a disk about the width of a dinner plate, there are 5,000 tiny robotic arms. Each one holds a single strand of optical fiber, thinner than a hair. When the telescope settles onto a new patch of sky, all 5,000 of those little arms begin to move at once. They swivel and reach and lock into position, each one aiming its fiber at the exact spot where the light of one specific galaxy will land. The sound, if you were standing close enough to hear it, is a soft mechanical whisper, 5,000 small motors moving together in the dark. It takes only a couple of minutes. Then the fibers drink in the light, carry it away to be split into its colors, and the arms reset. Every 20 minutes or so, the whole array reconfigures, and the telescope drinks another mouthful of the sky. Night after night after night, since the survey began in 2021, this machine has been collecting the light of galaxies. Not photographs of them, but their spectra, the fingerprint you get when you spread a beam of light out into its full range of colors. And from those fingerprints, DESI has been building something that has never existed before in human history. It has been building the largest three-dimensional map of the universe ever assembled. On the 19th of March, in the year 2025, the collaboration that runs the instrument released the second major piece of that map. They called it Data Release 2, which is not a poetic name, but the thing itself is close to overwhelming. It contains the positions of roughly 15 million galaxies and quasars. It covers about 60% more sky than the first release did. And because looking out into space is the same as looking backward in time, this map does not just show us where things are now. It shows us how the universe has been behaving for the last 11 billion years, most of the age of the cosmos itself. I want you to sit with the strangeness of that for a second. because we say things like 11 billion years so casually that they stop meaning anything. Every galaxy on that map is a point of light that left its source before the Earth existed, before the Sun existed, in some cases before our galaxy had finished forming. When DESI captures one of those ancient beams, it is holding a piece of the past in its hand. Stack 15 million of those pieces together, in order, and you get something like a film of the universe expanding. You get a record of the cosmos breathing outward, frame by frame, across almost the entire span of time. That is the map. And a map, you would think, is a safe thing. A map does not have opinions. It does not make predictions. It just tells you what is there. If you had described this project to me before the results came out, I would have expected a triumph, a beautiful achievement, a lot of gorgeous images, and a press release full of superlatives. I would not have expected fear. But here is the thing about this particular map. When the scientists laid it down and compared it against everything we thought we knew about the universe, the map disagreed. Gently, quietly, at the very edge of what the numbers could support, it disagreed about the one thing we were most certain of. It disagreed about the substance that makes up most of reality, the substance we have been calling dark energy, the substance whose behavior decides whether the universe ends in cold, in fire, or in a collapse back to where it began. For 25 years, we had assumed that this substance was a constant, fixed, unchanging, the one steady thing in a restless cosmos. It was the assumption everything else was built on top of, the flat foundation under the whole house of modern cosmology. And the map, drawn by 5,000 little robotic arms in the Arizona dark, suggested that the foundation might be moving. The people in that collaboration are careful people. They are not prone to drama. And so the phrase they reached for was deliberately restrained. They did not say, "We have discovered that dark energy is changing." They said there was, in their words, more than a hint. More than a hint that the thing holding the universe's fate in its hands is not standing still after all. You are going to hear that phrase again before this is over, because it matters. More than a hint. Not a proof, not a certainty, but more than nothing, and more than they expected, and more than the standard story of the universe is supposed to allow. A hint, held up against the largest map ever made, that the ending we thought was written has quietly come unwritten. It is worth pausing on just how much looking went into that map, because the scale of the effort is part of what makes the results so hard to wave away. This is not one astronomer with one telescope on one clear night. It is an international collaboration of hundreds of scientists across dozens of institutions, running a machine that gathers the light of tens of thousands of galaxies every single night it operates. Over the first 3 years, it collected tens of millions of individual spectra, each one a full rainbow of a distant object's light, teased apart and measured. To appreciate the leap, consider that the great galaxy surveys of the previous generation, the ones that first proved this technique could work at all, mapped a few 100,000 galaxies and were rightly celebrated as landmarks. This instrument gathered more galaxies than all of those earlier surveys combined, and it did it in a handful of years. There is a reason the collaboration built something so extreme, and it comes back to the tilt we are chasing. To measure whether dark energy changes over time, you cannot look at one distance or one era. You have to measure the expansion of the universe at many different epochs, precisely, and then compare them. A small map gives you a blurry, uncertain curve, one that could be tilted or flat depending on how you squint at it. A map of 15 million galaxies gives you a curve sharp enough to tell the difference between a universe that is holding steady and one that is quietly changing its mind. The whole point of the machine was to turn a question that used to be a matter of opinion into a matter of measurement. So when this instrument, built specifically and only to pin down the behavior of dark energy, returned an answer that disagreed with the flat line, it carried a particular kind of weight. This was not an accident stumbled upon by a telescope pointed at something else. This was the most sensitive tool ever built for exactly this purpose, telling us that the thing it was designed to measure is not behaving the way we assumed. A picture of the cosmos more complete than anything humanity had ever assembled had come back with a message no one ordered. So before we can understand why a map frightened the people who made it, we have to understand what they were measuring and why one small number buried inside it turned out to be the most important number there is. We have to understand what dark energy actually is, or rather, how little we actually know about the thing that rules the sky. That is where the ground starts to feel less solid under your feet, and it begins with a single line that the data simply refused to sit on. Part 2. The line the data would not sit on. To understand what went wrong with the map, you first have to understand what the scientists expected the map to say, and what they expected was a straight, flat line. For the last quarter of a century, cosmology has run on a model with a slightly clumsy name. It is called lambda cold dark matter, and most physicists shorten it to lambda CDM. You do not need to memorize that. You only need to know what the very first letter stands for, because that letter is the whole story. Lambda is a single Greek symbol, and it stands for the cosmological constant. It stands for the idea that dark energy is exactly that, a constant, a number that has the same value at every point in space and at every moment in time, from the birth of the universe to its final silence. The cosmological constant has a strange and almost embarrassing history, which we will come back to. But for our purposes right now, the important thing is how well it has worked. This one assumption, that dark energy is a fixed constant, has quietly fit almost every observation cosmologists have thrown at it for 25 years. The pattern of light left over from the Big Bang, the way galaxies cluster together into walls and filaments, the brightness of exploding stars halfway across the universe, all of it lined up with a model in which dark energy never changes. When something works that well for that long, you stop questioning it. It stops being an assumption and starts feeling like a fact. So when the DESI team took their new map and asked it the obvious question, they expected the obvious answer. The question was simple. How has the expansion of the universe changed over time? And the model predicted a specific, boring shape. If dark energy is truly a constant, then when you plot its behavior across the history of the cosmos, you should get a perfectly flat line. No bumps, no slope, no drift. The same value 11 billion years ago as today and forever after. Flat, like the surface of still water. The map did not give them a flat line. When they measured the expansion history epoch by epoch and fit it against the data, the best description was not a constant at all. It was a value that changes with time, and the direction of that change is the unsettling part. The data preferred a dark energy that was slightly stronger in the distant past, and has been weakening as the universe has aged. The flat line that should have been dead level had, ever so slightly, begun to tilt. Now, I want to be honest with you about the size of this effect, because the honesty is part of what makes it fascinating rather than frightening. This is not a case of the map screaming that everything is wrong. It is a case of the map whispering that something is a little off, and the whisper being just loud enough that the scientists could not talk themselves out of hearing it. The tilt is small. The wiggle away from the flat line is subtle. If it were larger, frankly, it would be easier to dismiss as an obvious mistake. It is precisely because it sits in that uncomfortable middle zone, too big to ignore and too small to fully trust, that it has thrown the field into such a productive kind of turmoil. Here is a way to feel what happened. Imagine you have weighed yourself every single morning for 25 years on the same scale, and the number has always been the same, to the ounce, without fail. It has been so reliable that you have stopped really looking at it. Then one week, the number is a tiny bit different, not dramatically, just enough that you notice. Your first instinct is that the scale is wrong, or the floor is uneven, or you stepped on it strangely, and most of the time you would be right. But then you check the scale and the floor and your footing, and the number stays a tiny bit different, day after day. At some point, the boring explanations run out, and you are left holding a small, stubborn discrepancy that will not go away. That is roughly where cosmology found itself when Desi's map came back tilted instead of flat. The tilt has a technical description, which we will unpack properly in a little while, because it is where the real strangeness lives. But the plain language version is the one that should keep you listening. The map suggested that dark energy, the dominant ingredient of the entire universe, the thing that outweighs every star and every atom and every wisp of dark matter combined, is not a fixed feature of reality. It looks like it might be fading, and if it is fading, then everything downstream of it changes. Because dark energy is not just some minor character in the story of the cosmos. It is the engine of the universe's future. It is the thing pushing everything apart, deciding how fast the sky empties out, deciding whether the expansion runs away forever, or slows, or stops, or reverses. Change the engine, and you change the destination. A flat line meant one ending. A tilted line means the ending is up for grabs. The letter at the front of the model has a history that makes this moment even richer, and it is worth telling because it means the universe may be playing the same trick on us twice. The cosmological constant was not invented to explain dark energy. It was invented by Albert Einstein in 1917 for the opposite reason. Einstein had just written down his theory of gravity, and when he applied it to the whole universe, the equations insisted that the cosmos could not sit still. It had to be either expanding or contracting. But at the time, everyone, including Einstein, believed the universe was static, eternal, and unchanging. So he added a term to his equations by hand, a constant, to hold the universe still, to balance gravity and keep everything in place. That term was lambda. Then, in 1929, Edwin Hubble showed that the universe is not static at all. The galaxies are flying apart. The universe is expanding, exactly as the original, undoctored equations had tried to say. Einstein, the story goes, called the cosmological constant the biggest blunder of his life, and threw it away. He had bent his own theory to fit a belief about the universe that turned out to be wrong, and in doing so, he had missed the chance to predict the expansion before anyone observed it. And here is the twist that should make the hair on your neck stand up. That discarded term, Einstein's great blunder, is the very same lambda that came roaring back in 1998 to describe dark energy. The thing he invented to hold the universe still was resurrected to explain why the universe is flying apart faster and faster. Physics reached into the trash, pulled out the one idea Einstein regretted most, and made it the foundation of modern cosmology, and it worked. With lambda restored as a constant, the model fit the ancient light of the Big Bang, the way galaxies cluster into a cosmic web, the abundances of the lightest elements, everything. For 25 years, the blunder was the bedrock, which is exactly why the tilt is so unsettling. We have already been embarrassed once by assuming we knew how the universe behaves on the largest scales. We assumed it was static and it was expanding. Now we have assumed the dark energy driving that expansion is constant, and the map is hinting that it moves. It would be a strange kind of poetry if the same term, in the same equations, fooled us in two opposite directions across a single century. But you cannot overturn 25 years of settled science on a whisper. The scientists knew that better than anyone. So before they were willing to say a single word out loud, they had to be sure that the tilt was real, that it was not a trick of one bad batch of data, and that it survived when they added more galaxies, more sky, more history. What they found when they checked is the reason a quiet map became the loudest result in cosmology in a generation. and it starts with the moment they decided to stop whispering. Part 3. More than a hint. The scientists did not trust the tilt at first, and that distrust is exactly why we should trust them. When a single measurement disagrees with a model that has worked for 25 years, the responsible response is not excitement, it is suspicion. The first thing any good cosmologist assumes is that they have made a mistake. So the DESI team did the thing you are supposed to do. They tried to make the tilt go away. They combined their map with completely independent measurements of the universe, made by different instruments, using different physics, sensitive to different kinds of error. The idea is simple. If several unrelated ways of looking at the cosmos all point in the same direction, the chance that they are all being fooled in the same way at the same time drops toward nothing. They had 3 ropes to braid together. The first was their own map, the pattern of galaxies stretching back 11 billion years. The second was the oldest light in existence, the faint glow left over from the Big Bang itself, released when the universe was less than 400,000 years old. That light carries a snapshot of the infant cosmos and sets the starting conditions for everything that followed. The third rope was exploding stars, a particular kind of supernova that flares with almost the same true brightness every time, which lets astronomers use them as markers to measure cosmic distances directly. Any one of those 3, on its own, only whispers. But when the scientists laid them against each other, the whispers did not cancel out. They reinforced. Together, the 3 lines of evidence preferred a universe with changing, weakening dark energy over the old flatline model. And the strength of that preference landed in a very particular and very uncomfortable range. In physics, confidence gets measured in a unit called sigma. You do not need the mathematics. You only need the ladder. 3 sigma means there is roughly a 1 in 700 chance that what you are seeing is a random fluke. That is enough to make people sit up, but not enough to bet the house. 5 sigma, much further up the ladder, means about 1 chance in 3.5 million, and that is the bar physics demands before it will use the word discovery. It is the bar the Higgs boson had to clear. The DESI result for evolving dark energy sits between roughly 3 sigma and just past 4 sigma, depending on which batch of supernovae they fold in, which means it lives in that maddening middle country, too strong to shrug off, too weak to carve into stone. So the temptation, still, was to wait for it to disappear. New results in that middle zone very often do. And this is where the story turns, because they got a natural test of exactly that. The March 2025 map, Data Release 2, was not the first version. A year earlier, in 2024, they had released a smaller map with fewer galaxies, and it had shown the same faint tilt. The obvious hope was that the tilt was just noise from not having enough data yet, and that when they gathered more, it would melt back into the flat line where it belonged. They more than doubled the data. They added years of observations, millions more galaxies, and a great deal more sky. And this is the part that changed the mood in the room. The tilt did not melt. If anything, it firmed up. A statistical fluke is supposed to fade when you pour more data on top of it, the way a mirage thins as you get closer. This one did the opposite. It stood its ground. That is when the careful people allowed themselves a careful sentence. They said the data showed more than a hint that dark energy is evolving. Read that phrasing again, because every word in it is doing a job. More than a hint is not a discovery, and they were scrupulous about not pretending it was. But it is also not nothing, and it is not what a healthy standard model is supposed to produce. It is the sound of a 25-year-old certainty developing a hairline crack and refusing to seal back up no matter how much data you throw at it. I want to give you a phrase to hold on to through the rest of this, because the scientists are effectively holding on to it too. A hint, not a headline. That is the discipline this result demands. It would be easy, and it would get a lot of attention to say the universe is definitely dying differently than we thought. It would also be dishonest. What is actually true is quieter and, to my mind, stranger. We have found something that looks like the beginning of an answer to the biggest question there is, and we are not yet allowed to be sure of it. A hint, not a headline. Keep it in your pocket. I want to say a little more about those 3 ropes, because the way they were braided together is the difference between a rumor and a result. The map of galaxies, on its own, is powerful but incomplete. It measures the ancient sound wave ruler at many distances, but to turn that into a full history of the expansion, it helps to know 2 things the map alone cannot pin down perfectly. That is where the other 2 ropes come in. The oldest light in the universe, that faint glow from 400,000 years after the Big Bang, fixes the starting conditions, essentially telling us how big the ruler was to begin with. And the exploding stars give an independent handle on the recent expansion, the last several billion years, where dark energy has done most of its work. Each rope is strong where the others are weak. The exploding star rope, it turns out, is also the one that stirs up the most argument, and the collaboration was careful to say so. There is not one single catalogue of these supernovae. There are several, assembled by different teams over different years, each with its own careful corrections and its own quirks, and when the DESI team combined their map with one catalogue, the preference for changing dark energy came out around 3 sigma. When they used another, it climbed higher, toward 4. The scientists reported all of these combinations openly, rather than quietly choosing the most dramatic one, which is exactly the behavior that should make you trust them more, not less. They were showing their work, including the parts that make the result look shakier. What none of the combinations did was make the tilt disappear. Whichever way they sliced it, whichever supernova catalogue they folded in, the data kept preferring a dark energy that changes over a dark energy that stays fixed. The strength of that preference wobbled between merely interesting and genuinely provocative, but the direction never flipped. And crucially, the anchor rope, the ancient light from the Big Bang, is about as clean and well understood a measurement as exists in all of cosmology. When your most trusted rope and your most argued over rope both pull in the same direction, you start to run out of comfortable ways to dismiss the result. The comparison between the 2 releases is really the spine of the whole case, so let me lay it out plainly. In 2024, the first release fit a smaller map against the same independent measurements, and it produced a preference for evolving dark energy that made headlines and raised eyebrows in equal measure. The natural, cautious expectation among many cosmologists was that this was an early data mirage. Early results in any survey are noisier, drawn from less sky and fewer objects, and they have a well-earned reputation for shifting once the full picture comes in. Plenty of physicists quietly bet that the second release would pull the result back toward the boring flat line, and honestly, that would have been the more comfortable outcome for everyone. A tidy universe is easier to teach. Then the second release arrived a year later, with more than double the galaxies, a substantially larger slice of the sky, and years of additional observation folded in. This was the moment the mirage was supposed to evaporate. Instead, the preference for changing dark energy held firm, and, by some measures, grew a little sharper. The people running the collaboration were, if anything, more careful in how they described it the second time, precisely because they knew how it would be heard. They did not hold a triumphant press conference, declaring the universe rewritten. They published the numbers, showed every combination, flagged every caveat, and let the restraint of their language carry the weight. That restraint is itself a kind of evidence. It is the sound of careful people who have checked their work and cannot make the strange thing go away. Because here is what makes even the hint so heavy. It is not heavy because of the numbers. It is heavy because of what the numbers are about. To feel the full weight of a weakening dark energy, you have to understand what dark energy is in the first place. And the honest answer to that question is one of the most humbling admissions in all of science. We gave this thing a name. We measured how much of the universe it makes up. We built the entire future of the cosmos on top of it, and we have never had the faintest idea what it actually is. Part 4. The thing we named but never knew. The story of dark energy begins with a mistake that everyone expected to make, and a result that no one was ready for. Rewind to the late 1990s. Two rival teams of astronomers were racing to measure something that felt almost routine. They wanted to know how fast the expansion of the universe was slowing down. Notice the assumption baked into that sentence. Everyone knew the universe was expanding, that had been settled since the 1920s. And everyone assumed that the expansion had to be slowing, because the universe is full of matter, and matter has gravity, and gravity pulls things together. The only real question, people thought, was whether gravity would eventually win and pull everything back, or whether the universe would coast outward forever, slowing but never quite stopping. Either way, the expansion had to be losing speed. The teams were just there to measure how quickly. To do it, they used a special kind of exploding star. When a certain type of dead star reaches a precise tipping point and detonates, it flares with very nearly the same true brightness every single time. Astronomers call these Type 1 a supernovae, and because their real brightness is so predictable, you can tell how far away one is by how dim it looks from here. Catch enough of them at different distances, and you can reconstruct how the expansion of the universe has changed over billions of years. So, both teams went hunting for these distant explosions, fully expecting to watch the cosmic expansion putting on the brakes. COVID 1998, they found the opposite. The distant supernovae were dimmer than they should have been, which meant they were farther away than the slowing down picture allowed. The only way to make the numbers work was almost too strange to say out loud. The expansion of the universe was not slowing down, it was speeding up. Something was pushing the cosmos apart, harder and harder, overpowering the gravity of every galaxy in existence. Both teams, checking each other, arrived at the same impossible conclusion. The discovery was so important and so unexpected that it won the Nobel Prize in Physics in 2011. They needed a name for whatever was doing the pushing, and the name they chose was a confession dressed up as a term. They called it dark energy. Dark, not because it is black, but because we cannot see it and we do not understand it. The name describes our ignorance, not the thing itself. We had discovered the single most powerful influence in the universe, and in the same breath admitted we had no idea what it was. Then came the truly humbling part, the accounting. When cosmologists added everything up, they found that dark energy is not a minor player. It is the majority of the universe. Roughly 68 to 69% of the total energy of the cosmos is this dark energy we cannot identify. Another 27% or so is dark matter, a different mystery, some unseen substance that holds galaxies together, which leaves everything else. Every star you have ever seen, every planet, every mountain and ocean, every atom in your body and in the body of everyone you have ever loved, all of the ordinary matter in all of existence, adds up to about 5% of what is out there. I want you to really let that settle, because it is the first place in this story where the ground genuinely drops away. 95% of the universe is made of things we cannot see and do not understand. And the largest single slice of it, the piece that outweighs all the stars and all the galaxies combined, is a substance whose name is literally an admission that we are in the dark. We are not the main characters in the universe. We are not even made of the main ingredient. We are the 5%, the thin, bright foam on top of an ocean of two mysteries, and we have been telling ourselves stories about how it all ends while standing on a floor we have never been able to see. And it gets worse, or better, depending on your appetite for these things. Physicists did try to explain what dark energy might be. The most natural guess was that it is the energy of empty space itself. According to quantum physics, a perfect vacuum is not truly empty. It seethes with fields that carry a baseline energy even when nothing is there. That energy would push outward exactly the way dark energy does. It seemed almost too neat. So they calculated how much energy empty space should contain, and the answer was a catastrophe. The number that quantum theory predicts for the energy of the vacuum is larger than the amount we actually observe by a factor so enormous it is difficult to write down. We are talking about a mismatch of around 10 to the 120th power, a 1 followed by 120 zeros. It is routinely called the worst prediction in the history of physics, the largest gap between theory and reality that science has ever produced. So here is where we actually stood before the map ever came back tilted. We had a substance that makes up most of the universe. We could not see it. We could not explain where it comes from. Our best theory for it missed by a factor of 10 to the 120th power, and in the face of all that ignorance, we did the only thing we could do to keep the equations working. We assumed it was simple. We assumed that whatever dark energy is, at least it does not change. We made it the one fixed thing in a universe where everything else moves, the steady flame we could build the future around. We could not say what it was, but we told ourselves, at least, that it would always be the same. I skated past the drama of that 1998 discovery, and it deserves a moment, because it shows how reluctantly science accepts a thing this strange. The two teams were rivals, working separately, almost suspicious of each other. One was led out of a national laboratory in California, the other assembled from astronomers scattered across the world. Both were hunting the same distant explosions, and both, independently, watched their numbers arrive at the same impossible place. And the first reaction, in both camps, was not joy. It was dread that they had made an error. The astronomers went looking for the mistake. They checked whether cosmic dust was dimming the supernovae and faking the result. They checked whether ancient exploding stars might simply be different from nearby ones. They checked their calibrations, their assumptions, their arithmetic. The acceleration survived every check. Only when they could not make it go away did they let themselves believe it, and even then they published it with visible unease. That is how a Nobel Prize is supposed to feel on the way in. Not like a triumph, but like a fact you cannot argue your way out of. The vacuum energy idea deserves a second look too, because it is where the humility really bites. When quantum physics says that empty space seethes with energy, it is not being poetic. Particles are constantly flickering in and out of existence everywhere, even in a perfect void, and each of those flickers carries energy. Add it all up, and empty space should be dense with it. The trouble is only in the amount. The theory does not miss by a little. It misses by that factor of 10 to the 120th power, a gap so enormous that if the prediction were right, the universe would have torn itself apart before a single galaxy could form. Something must be cancelling almost all of that energy, to an accuracy of more than 100 decimal places, leaving just the faint trace we actually measure. We do not know what does the cancelling. We do not know why it stops where it does. There is one more twist of the knife, and physicists call it the coincidence problem. Dark energy stays roughly constant per unit of space, while matter thins out as the universe expands. So for almost all of cosmic history, one of them has utterly dominated the other. And yet we happen to live at the brief, strange moment when the two are comparable, when matter has just recently given way to dark energy as the ruler of the cosmos. Out of all the eras we could have found ourselves in, we are here for the handover, whether that is a clue or just luck, no one can say. The map is the thing that came back and asked, quietly, whether even that was true. And to understand what the map actually measured, we have to look at the single number that carries the entire question, one number that decides, all by itself, how the universe ends. Part 5. The one number that decides everything. Everything we have been circling comes down to a single letter. Physicists call it W, and it is, without exaggeration, one number that decides how the universe ends. Let me build up to what W means, because once you feel it, you cannot unfeel it, and the rest of this story becomes almost unbearably suspenseful. Dark energy pushes space apart. But to predict the future of the universe, it is not enough to know that it pushes. You have to know how its push behaves as the universe grows. Does the push stay the same as space expands? Does it get stronger? Does it get weaker? That behavior, the relationship between dark energy's pressure and its density, is captured entirely by the value of W. It is the single dial that tunes the fate of everything. The critical setting on that dial is -1. Write it down in your mind. -1. If W is exactly -1, then dark energy is a true cosmological constant, the energy of empty space, and it has a very particular property. As the universe expands and makes new space, that new space comes with its own dark energy, so the density never dilutes. There is always exactly as much push per volume as there ever was. The universe accelerates at a steady, unchanging rate forever. That is the flat line. That is the value the Standard Model has assumed for 25 years. -1, holding perfectly still. Now watch what happens when the dial moves, even slightly, because this is where the endings live. Suppose W is a little greater than -1, somewhere between -1 and about -1/3. Now, dark energy is not a fixed constant. It is more like a substance that thins out as the universe grows. Its push weakens over time. The acceleration slows down. Physicists call this kind of dark energy quintessence, after the old idea of a fifth element beyond earth, water, air, and fire. In a quintessence universe, the engine of expansion is gradually running out of pressure. The future is gentler, slower, and crucially, it is not guaranteed to run away forever. Now push the dial the other way. Suppose W is a little less than -1. This is a genuinely bizarre regime, and physicists gave it a genuinely bizarre name. They call it phantom energy. If W is below -1, then as the universe expands, the density of dark energy does not stay constant and does not thin out, it increases. The more space there is, the more violently that space pushes itself apart, which creates even more space, which pushes even harder. It is a runaway, and a runaway like that does not end quietly. It ends by tearing the universe to pieces, in a scenario we will come to, called the Big Rip. So look at what this one number is holding. If W sits exactly on -1, you get the cold, endless drift of a steady expansion. If W rides above -1, you get a weakening push and a gentler, more open future. If W drops below -1, you get a runaway that rips reality apart. 3 completely different endings for the universe, and the only thing separating them is which side of a single value one number happens to land on. -1 is not just a number, it is a knife edge. It is the border between 3 different apocalypses. For 25 years, we assumed the universe was balanced perfectly on that edge, at exactly -1, and staying there. That is an extraordinary thing to assume when you say it plainly. We assumed the universe had chosen the one razor-thin value that sits precisely between weakening and runaway, and that it would hold that value with perfect discipline until the end of time. The DESI map was, in the end, a machine for measuring W, not just W today, but how W has changed across cosmic history. Cosmologists describe that with two numbers instead of one. There is W0, the value of the dial right now, in the present-day universe, and there is W, which measures how much the dial has been moving over time. In the old model, both are fixed. 10 is -1, and WA is 0, meaning no change at all. A flat line needs those two values, -1 and 0, locked in place. The map did not return -1 and 0. When the scientists let the two numbers float and asked the data what it preferred, the answer came back with W0 sitting above -1 and WA sitting below 0. In plain terms, the map said that dark energy today is on the quintessence side of the knife edge, the weakening side, and that it has been sliding in that direction over time. It also said something stranger, hidden in those numbers, which is that in the distant past, dark energy may have been on the phantom side, below -1, and has since crossed over. We will come back to that crossing, because it is the part that keeps physicists up at night. But sit for a moment with just the headline, because the headline alone is staggering. We built our entire picture of the universe's fate on the assumption that W equals -1 and never moves. The largest map ever made looked back across 11 billion years and reported that W does not appear to be sitting on -1 and does not appear to be holding still. The dial that decides how everything ends is apparently turning. I have been saying that dark energy pushes, but the way it pushes is stranger than a simple shove, and W is really a measure of that strangeness. In everyday life, pressure pushes outward. The air in a balloon presses against the walls. But dark energy does something that has almost no parallel in ordinary experience. It has negative pressure. It pulls inward on itself, like a stretched rubber sheet under tension. And here is the counterintuitive core of it, the thing that trips almost everyone. In Einstein's theory of gravity, pressure has weight. Ordinary outward pressure actually adds to gravity, pulling things together. So negative pressure, tension, does the reverse. It pushes space apart. That is why a substance with a value of W near -1, all tension, and no ordinary matter, drives the universe to expand faster instead of slower. The number W is really telling you how much tension the emptiness of space is under. Once you see it that way, the knife edge at -1 takes on an even sharper meaning. -1 is the exact value where the tension of empty space is perfectly matched to its energy, the balance point of a true cosmological constant. Sit precisely there, and the vacuum has just enough tension to push at a steady, eternal rate. Drift above it, and the tension is a little weaker than the energy, so the push fades. Drop below it, into the phantom country, and the tension outruns the energy in a way that feeds on itself. One value, and everything around it is a different destiny. And now think about how astonishing it is that we ever believed the universe was sitting exactly on that value. There is nothing in any theory that requires W to be precisely -1. It could, in principle, be -0.9 or -1.1 or anything at all. For the universe to land on -1 and hold, there would be a coincidence of almost unimaginable precision, like a pencil balanced perfectly on its point for the entire age of the cosmos. Physicists accepted it not because it was natural, but because it was simple and because the data had not yet forced them to consider anything else. The map is the first thing that has genuinely forced the question. It is asking whether the pencil was ever really balanced, or whether it has been slowly, quietly falling this whole time, which raises an obvious and slightly maddening question. How on earth do you measure the pressure of an invisible substance that fills all of space across 11 billion years of history from a mountaintop in Arizona? You cannot put dark energy on a scale. You cannot squeeze it in a laboratory. And yet the scientists are quoting you the value of its inner dial to within a few tenths. The answer to how they do it is one of the most quietly beautiful pieces of physics I know, and it depends on a sound that rang out when the universe was a newborn and then froze into the sky forever. Part 6. A ruler made of sound. The ruler that measured dark energy is not made of metal. It is made of sound, and it is older than every star in the sky. To understand it, I want to take you back to the earliest chapter of the universe, and I want you to experience it rather than just hear about it. So close your eyes, if you are somewhere you can, and come with me to a time before there were any stars at all. You are inside the universe when it is very young, less than 400,000 years old. There is no darkness here, and there is nowhere to stand. Everything is a single glowing fog, a plasma so hot and so dense that light itself cannot travel freely. It keeps colliding with particles and scattering, so the whole cosmos glows from within the color of a furnace in every direction at once. You are not looking at this fog. You are suspended inside it, and it presses on you from all sides, warm and blinding and humming with pressure. Now, somewhere near you, gravity has pulled a little extra matter into a slightly denser clump, and that clump does something wonderful. It pushes back. The heat and light trapped inside it create an outward pressure, and that pressure launches a wave, a spreading ripple of matter and radiation rolling outward through the fog in every direction, like the sound of a struck bell moving through air. Because that is exactly what it is. It is a sound wave, a real one, rolling outward through the substance of the newborn universe at more than half the speed of light. All across the cosmos, countless of these waves are spreading from countless dense spots, an ocean of overlapping ripples ringing through the fire. Feel the texture of this place for a moment longer, because nothing about it resembles the universe you know. There is no up and no down, no empty space to fall through, only the dense, luminous substance pressing in from everywhere at once, hotter than the core of any star that will ever exist. The waves rolling through it are not gentle. They are the loudest thing the universe will ever contain, a pressure so total that matter and light move together as a single fluid, sloshing and ringing. And this ringing is not chaos. It is structured, almost musical, a set of tones set by the size and age of the infant cosmos, a chord being held across the entire universe at the same instant. If you could somehow hear it, you would be hearing the one and only sound the universe ever made while it was young enough to make one. And then the universe cools, and everything changes in an instant. As the fog thins, the moment arrives when atoms can finally form, and light breaks free to travel. The pressure that was driving the waves suddenly vanishes, and every one of those expanding ripples freezes exactly where it is, like a photograph of a splash caught in mid-air. Each wave leaves behind a faint spherical shell of slightly denser matter, frozen into the cooling universe at the exact radius it had reached in that final instant. That radius, that frozen size, is always the same. It is set by how far a sound wave could travel in the young universe before the music stopped, and it comes out to roughly 490 million light-years across. Open your eyes, because those frozen shells never went away. As the universe expanded and matter gathered into galaxies, galaxies were very slightly more likely to form on those denser shells. So even today, if you map millions of galaxies, you find a faint preferred distance between them, a subtle extra clumping at that same characteristic scale, the fossil of a sound wave from the dawn of time. Cosmologists call this pattern baryon acoustic oscillations, which is a mouthful, but the idea underneath it is almost unbearably elegant. Printed into the arrangement of the galaxies is a ruler of a known and fixed length, a ruler made of ancient sound. And a ruler of known length is the most powerful tool an astronomer can have. Here is why. If you know how long something truly is, and you measure how large it appears in your sky, you can work out exactly how far away it is. Hold a familiar object at arm's length, and it looks a certain size. Move it across the room, and it looks smaller by a precise and predictable amount. The frozen sound wave scale works the same way. Cosmologists know its real length from the physics of the early universe. So when they measure how large that scale appears among galaxies at different distances, they can read off how far away those galaxies are, and how fast the universe was expanding when that light set out. This is what the DESI map really is. It is not just a pretty scatter of 15 million points. It is 15 million galaxies, sorted by distance, each one carrying that ancient ruler printed into its neighborhood. Nearby galaxies show the ruler as it looks in the recent universe. Galaxies billions of light years away show the ruler as it looked billions of years ago. Line them all up in order, and you are not looking at a snapshot. You are watching the expansion of the universe change, epoch by epoch, across 11 billion years. You are watching the history of the push itself. And that is how you weigh the pressure of an invisible thing from a mountaintop in Arizona. You do not touch the dark energy. You watch what it has done to the spacing of the galaxies over cosmic time, using a ruler that the universe was kind enough to leave lying around inside itself. The steadiness of that method is the reason the tilt in the data is so hard to dismiss. It is not one measurement. It is the same ancient ruler, read at hundreds of different distances, and every reading together traces out the shape of how dark energy has behaved. There is a beautiful piece of confirmation hiding inside all of this, and it is worth knowing because it is the reason cosmologists trust the ancient ruler so completely. Those same frozen sound waves left a second fingerprint in a completely different place. Remember that when the fog of the early universe cleared, the light that broke free is still traveling today as that faint glow from the Big Bang, and that glow is not perfectly smooth. It carries a pattern of slightly hotter and slightly cooler patches, and the characteristic size of those patches is set by the very same sound waves caught at the very same instant they froze. So the ruler shows up twice. Once as a preferred spacing between galaxies, measured by mapping the recent universe, and once as a preferred size of ripples in the oldest light, measured from the infant universe. Two completely different observations of two completely different things, billions of years apart, and they agree on the length of the ruler. When a measurement checks out like that, from two directions at once, you stop worrying that you have imagined it. The technique also has a track record. The first clear detection of these frozen sound waves in the distribution of galaxies came around 2005 from an earlier survey, and it was hailed as a triumph precisely because it confirmed a prediction made decades before. Since then, survey after survey has measured the ruler with growing precision, and it has behaved exactly as the physics said it should. The DESI map is the latest and largest entry in that lineage, not a lone strange claim, but the sharpest reading yet of a tool astronomers have been refining for 20 years. That lineage matters because it means the instrument that detected the tilt was not some untested gadget. It was the most trusted ruler in cosmology, wielded with more galaxies than ever before. And that is what makes the shape of the curve so hard to explain away. The scientists were not reading tea leaves. They were reading a ruler they understand from two independent directions, at hundreds of distances, with a method that has been validated over and over. So when the readings lined up into a curve, everyone paid very close attention to what that curve actually looked like. When they traced that shape, it did not hold flat at -1. It drifted, and the direction of the drift is the thing we now have to face directly because it is stranger than a simple weakening. The map does not just say dark energy is fading. It says dark energy may have crossed a line that, according to our simplest physics, nothing should be able to cross. That crossing is where the mystery stops being about a number and starts being about the nature of empty space itself. Part 7. The Weakening. The map did not simply say that dark energy is weakening. It said that dark energy may have done something that our simplest physics says is impossible. It crossed the line. Remember the two numbers, W0 and WA. When 0 came back above -1, on the quintessence side, the weakening side. But WA, the rate of change, came back negative, meaning dark energy has been sliding downward in strength over time. Follow that slide backward into the past, and you reach an uncomfortable implication. If the push is above -1 now and has been decreasing, then earlier in cosmic history it may have been sitting below -1 on the phantom side. Which means that somewhere in the middle of the universe's life, dark energy would have had to pass through the value of exactly -1, moving from the phantom regime up into the quintessence regime. Physicists call this the phantom crossing, and it is the detail that turns an interesting result into a genuinely strange one. Here is why the crossing matters so much. The most natural way to build a changing dark energy is to imagine a single field filling all of space, slowly rolling like a ball easing down a gentle slope. This is the quintessence idea, and it is elegant and simple. But a single rolling field of that kind has a hard rule. It can sit above -1, or it can approach -1, but it cannot cross to the other side. The value -1 is a wall for it, a boundary it physically cannot pass through. So if the universe really did carry dark energy from below -1 to above it, then the simplest possible explanation is ruled out. You need something more elaborate. You need two fields interacting, a setup physicists half-jokingly call quintom, from quintessence plus phantom. Or you need to modify gravity itself to change Einstein's equations on the largest scales. Or you need something no one has written down yet. Do you feel what just happened there? We started this journey trying to measure one number. Now the map is not just handing us a strange value for that number. It is telling us that whatever dark energy is, it is more complicated than the simplest thing it could possibly be. The universe reached into its bag of explanations and pulled out one of the weird ones. And now I want to slow all the way down and let you feel this from the inside, because the numbers can make it sound abstract when it is anything but. So come and stand on a single galaxy with me, and we will run time forward and watch the weakening happen. You are anchored to one ordinary galaxy, somewhere in the middle of cosmic history. Around you, the sky is full of other galaxies, and every one of them is drifting away from you as the space between you stretches. In the early stretch of this journey, the drift is quickening. The distant galaxies are receding faster and faster, their light stretching redder as they go, some of them accelerating so hard toward the horizon that their light is beginning to lose the race to reach you at all. The push is strong here. Space is being manufactured between you and everything else at a growing rate, and the universe feels like it is straining outward, more violently with every passing billion years. And then, so slowly that you would never notice it in a single lifetime or a single civilization, something shifts, the quickening eases. The galaxies are still receding, space is still stretching, but the ferocity behind it begins, almost imperceptibly, to relax. The reddening light of the most distant galaxies stops racing away quite so fast. For the first time in the entire history of the cosmos, the outward push is not growing. It is loosening its grip. Nothing dramatic happens. No sound, no flash. Just a great cosmic exhale, a tension that has been building since the beginning, starting, gently, to let go. That loosening is what the map may have caught. And I think it is worth naming what makes it land so heavily, beyond all the physics. For 25 years, dark energy was the one thing we trusted to never change. Stars are born and die, galaxies collide and merge, continents drift, species come and go, even the protons in your body will not last forever. We knew all of that was in motion. But dark energy, the energy of empty space, was supposed to be the exception. It was the one fixed thing, the steady floor beneath all the motion, the part of reality you could set your watch by until the end of time. The map is suggesting that even that is moving. And there is something quietly overwhelming about that, if you let it reach you. It means there may be nothing in the universe that holds perfectly still. It means that emptiness itself, the vacuum, the nothing between the somethings, is not inert. It has a history, it has a behavior, it may have a future different from its past. We reached for the most solid thing we could imagine, more solid than any star or stone, and we chose the emptiness of space itself, and the emptiness turned out to have a mind of its own. I want to linger on how much trouble that phantom crossing causes, because it is where the result stops being merely surprising and starts being a genuine problem for our theories. The neat, minimal explanation for a changing dark energy was always a single field rolling down a slope, quintessence, and physicists liked it because it was economical. It asked for one new thing and no more. The crossing breaks that economy. To carry dark energy from below -1 up through the wall and out the other side, you need extra machinery, and every version of that machinery costs you something. Two fields interacting is more moving parts than anyone wanted. Modifying gravity itself is a far bigger step, because it means the theory that has passed every test for over a century, Einstein's general relativity, would be subtly wrong on the largest scales of all. Either way, the tidy picture is gone. The map is not just telling us dark energy changes. It is telling us that whatever dark energy is, it refuses to be the simplest thing we imagined. There is a real chance, then, that this result is pointing at something even bigger than dark energy. It may be pointing at gravity. For 100 years, we have assumed that Einstein's equations govern the cosmos unchanged, from the orbit of a planet to the expansion of the whole universe. But we have only ever tested those equations directly on relatively small scales, within our galaxy and its neighborhood. The behavior of dark energy is one of the few windows we have onto how gravity acts across billions of light years. If the window is showing us something strange, it may be that gravity has a few surprises left in it at scales we have never been able to probe. That is a genuinely unsettling possibility, because so much of what we believe about the universe rests on the assumption that the rules do not change with size. And step back once more to the feeling underneath all of this, because it is the real anchor of the whole story. We chose the emptiness of space as our one certainty, and now the emptiness is behaving in ways our best theories cannot cleanly explain, in ways that might even implicate gravity itself. The floor beneath the floor is moving. There is something almost vertiginous about realizing that the two most fundamental things we know, the vacuum and gravity, may both be hiding behavior we never suspected, and that a map of galaxies is the thing that caught them at it. None of this tells us yet how the story ends. It only tells us that the ending is no longer fixed, because the thing that writes the ending is no longer fixed. So, we have to do what cosmologists have quietly started doing since that March. We have to go back and reopen every possible fate of the universe, one by one, and ask how each of them changes if the push is fading. And the first ending we have to revisit is the one we were most sure of, the slow, cold, patient death that a steady dark energy was always supposed to deliver. Part 8. The ending made of cold. The ending we were most confident about is the coldest one. If dark energy had simply held at -1, the way we assumed, the universe was destined to die of cold. Physicists call it the heat death, or the big freeze, and for decades it was the quiet, almost boring consensus for how everything ends. Let me walk you into that future, because even though the map may be steering us away from it, you have to know this ending to understand what the weakening is rescuing us from, or condemning us to. A steady dark energy, holding at -1, means the universe accelerates apart forever at a constant rate. And forever, in this context, is a word with real teeth. Start with the sky. Right now, we can see billions of galaxies. But if the expansion keeps accelerating, every galaxy that is not gravitationally bound to our own local group will eventually be carried away faster than its light can cross the growing gap. One by one, over tens of billions of years, the distant galaxies will redden, dim, and slip past the edge of what we can ever see. The universe will not get smaller, but our view of it will. A civilization living 100 billion years from now, looking up, would see only the merged remains of our own local cluster of galaxies, floating in a sky that appears otherwise empty and black. All evidence that a wider universe ever existed would have receded beyond reach. The cosmos would spend eternity forgetting itself, then follow the stars. Star formation is already slowing across the universe, because galaxies are using up the gas they need to make new suns. Give it long enough, and the last star will form from the last usable cloud of gas. After that, it is only a matter of waiting for the existing stars to burn out. The bright, heavy stars go quickly. The small, dim red dwarfs are misers and can burn for trillions of years. But even they run down eventually. Somewhere around 100 trillion years from now, the last star gutters out and the universe goes dark for good. This is the beginning of what physicists call the degenerate era. A cosmos lit by nothing but the fading embers of dead stars, white dwarfs cooling to black, neutron stars going cold, everything sliding toward the same low temperature. And still the clock keeps running, into spans of time that make 1 trillion years look like an eye blink. Matter itself may not be stable across such stretches. If protons very slowly decay, as some theories suggest, then over a period so long, you have to write it as a 1, followed by 30 or 40 zeros, the dead stars and cold planets will slowly evaporate away into stray particles. What remains after that is a universe of black holes, the last massive object standing, and even black holes do not last. Through a subtle process first worked out by Stephen Hawking, black holes very slowly leak their energy away as faint radiation and shrink over unimaginable spans, until they too evaporate in a final flicker. The very largest of them take something like a 1 followed by 100 zeros in years to disappear. That number even has a nickname. A 1 followed by 100 zeros is called a googol, and that is roughly the lifespan of the last black hole. Try to stand at the far end of that timeline. Every star has died. Every black hole has evaporated. All the matter has thinned out and decayed. What is left is an almost perfectly empty space, filled only with a cold, sparse mist of stray particles and dim radiation, drifting ever farther apart, cooling toward a temperature just barely above absolute zero. Nothing happens anymore, because nothing is different enough from anything else to make anything happen. There is no light, no heat, no structure, no event. Just an endless, expanding, uniform, cold, growing, quieter, and emptier for the rest of time. That is the heat death. Not a bang, not a collapse, but a fading to a whisper that never quite reaches silence. I have always found this the loneliest of the endings, and for a long time it was the one most physicists expected. It is what a constant dark energy delivers. A universe that ends not by dying violently, but by spreading itself so thin and cooling itself so far that it simply runs out of the ability to do anything at all. An eternity of almost nothing. Physicists have actually mapped out the stages of this long dying, and giving them names makes the scale easier to hold. We live right now in what they call the stelliferous era, the age of stars, the brief, bright chapter when the universe is full of light. It began a few 100 million years after the Big Bang, and it will last, generously, a few tens of trillions of years. That sounds endless, but on the full timeline, it is barely the opening scene. After the last star fades, the universe enters the degenerate era, the long twilight of stellar corpses, white dwarfs, and neutron stars slowly cooling in the dark. Then, as even those decay away, comes the black hole era, when the largest black holes are the only significant structures left, slowly bleeding away their energy. And finally, the dark era, when even the black holes are gone and nothing remains but a thin, cold drift of stray particles. Each era is vastly longer than the one before, so that almost the entire future of the universe, if it freezes, is spent in near total darkness. The age of light is the shortest chapter of all. Underneath all of this is a single law doing the killing, and it is one you already know in your bones. It is the second law of thermodynamics, the rule that says things run down. Heat flows from hot to cold, never the reverse. Order decays into disorder. Every star, every living thing, every machine runs on a difference, a gradient, some hot thing next to some cold thing, and it survives by letting that difference even out. The heat death is simply the moment when every difference in the universe has finally been spent. Everything is the same temperature. There are no gradients left, nowhere for energy to flow, and so nothing can happen, not because the energy is gone, but because it is uselessly, perfectly, evenly spread. Physicists call that state maximum entropy. It is not an explosion or a collapse. It is the universe reaching a state so bland and so uniform that time itself stops meaning anything, because nothing ever changes again. That is the ending a constant dark energy hands you. Not a death by violence, but a death by sameness, a slow settling into a warmthless, eventless, endless calm. For a long time it was the ending most physicists quietly expected, and made a kind of peace with. There is a particular loneliness to imagining a conscious mind at the far end of that timeline, and it is worth sitting with, because it is what gives the heat death its emotional weight. Any beings living in the far future of a frozen universe would look out on a sky almost entirely dark, their own galaxy long since merged and cooled, every other galaxy carried beyond the horizon of sight. They would have no way of knowing the universe had ever been full of light and structure and neighbours. The evidence would be gone, receded past reach, and the story of everything that came before would be unrecoverable. A civilization born late enough into the freeze would conclude, reasonably and completely wrongly, that the universe had always been a small, dim, lonely place. The heat death does not just end the universe, it erases the memory of the universe having been anything else. But here is the turn, and it is the reason the map matters so much. The heat death was written for a universe with a fixed, unchanging push. It assumes dark energy holds at -1 forever. And the largest map ever made has just told us that dark energy may not be holding at -1. If the push is weakening, then this slow, cold ending is not necessarily our fate. Something is loosening the very force that was going to carry every galaxy out of sight and freeze the universe into that endless dark, which raises a question with an edge of hope and an edge of dread. If dark energy is not strong enough to freeze us, then what exactly is it strong enough to do? To answer that, we have to look at the ending we feared the most and ask whether the weakening has just taken it off the table. Part 9. The ending that tears. The ending we feared the most is the one that tears. Physicists gave it a name that sounds like a bad dream and behaves like one too. They call it the Big Rip, and for a while it looked like it might be our real future. The Big Rip lives in the Phantom regime, the strange country below -1 that we visited earlier. In 2003, a group of physicists worked out what would happen if dark energy were phantom energy, with a value of W below -1 that keeps getting more negative over time. The answer was violence on a scale that is difficult to hold in the mind. Remember that phantom energy grows denser as the universe expands. More space means more push, and more push means more space, in a feedback loop that does not level off. It accelerates. And if you follow that runaway to its conclusion, the push does not just grow large, it grows infinite in a finite amount of time. There is a last day. Let me take you to that last day, because you should feel what we may have just escaped. Come with me to the final stretch of a phantom universe, and we will watch it come apart from the outside in. It begins so gradually that no one would feel it, and then it does not stay gradual. In the final 100 million years, the push has grown so strong that it starts to overpower gravity itself, and it does so at larger scales first. Clusters of galaxies, held together for billions of years, begin to loosen and disperse, their members drifting apart into the growing dark. Then, in the last months, the disaster reaches inward to individual galaxies. Watch our own. The stars that have orbited the center in stately loops for eons begin to unwind, spiraling outward, the whole spiral structure fraying like a rope pulled apart strand by strand. The galaxy dissolves into the emptiness around it. Then it comes for the smaller things, and it comes fast. In the last hours, solar systems are pried apart, planets torn loose from their stars and flung into the dark. In the last minutes, watch a single planet, any planet, maybe a world very much like this one. The force holding it together loses to the push, and the planet comes apart, its oceans and its crust and its air lifting away in every direction at once. And, in the final fraction of a second, the tearing reaches the smallest scale of all. Molecules are pulled apart, then atoms, then the nuclei inside them. Everything that was ever bound to anything else is unbound, down to the last particle, and space itself is stretched to infinity. That is the Big Rip, an ending in which the universe does not fade or collapse, but is pulled so hard by its own emptiness that nothing is allowed to remain whole. For a couple of decades, this was not a fringe fantasy. It was a mainstream candidate for the real future of the universe, discussed in serious journals and worked out in careful detail, because the honest truth was that we could not rule it out. The measurements of dark energy were good enough to tell us it existed, and roughly how much there was, but not good enough to nail its value of W to the precision needed to say whether we were safe. As long as that number could plausibly sit a little below -1, the Big Rip stayed on the menu, a genuine possibility hanging over the far future like a sentence that had not yet been read aloud. Physicists do not scare easily, and even so, a paper titled around the idea of cosmic doomsday tends to concentrate the mind. It forced the field to take seriously the notion that the universe might have not just an ending, but a violent one, with a date attached. For years, this was a live possibility, a genuine candidate for our fate, because we simply did not know whether W was sitting above or below that fatal line. If dark energy were even slightly phantom, and getting more so, this is where we were headed. And here is the first piece of real relief the map has given us. The Big Rip requires dark energy to be below -1 and to keep sinking, growing ever more negative, driving the runaway. But the DESI map points the other way. It suggests that W today is above -1, on the gentler quintessence side, and that it has been rising, not falling. Even the hint that dark energy dipped into phantom territory in the distant past does not resurrect the rip, because a brief visit below the line long ago is not the same as a runaway plunge into the future. A universe whose dark energy is fading and climbing back above -1 is not a universe racing toward infinite push. The tearing needs the engine to roar louder and louder without limit. The map says the engine is getting quieter. The physicists who first worked this out even mapped the schedule of the destruction, and it is worth hearing because it turns an abstract horror into a countdown. In their worked example, they picked a phantom dark energy just modestly below the fatal line and calculated when each thing would come apart, counting backward from the final instant. About 1 billion years before the end, the push would grow strong enough to strip our galaxy away from the cluster around it. Around 60 million years before the end, it would tear our galaxy itself apart, unwinding the spiral. A few months before the end, it would pry the planets loose from the Sun, dismantling the solar system. About half an hour before the end, it would rip a planet like the Earth to pieces. And in the last unimaginably small fraction of a second, far less than the blink of an eye, it would tear apart the atoms themselves. A tidy schedule for the disassembly of everything, printed out in advance. What makes phantom energy so disturbing to physicists is not just the violence, but the way it breaks rules we thought were sacred. To have a value of W below -1, dark energy has to violate what are called the energy conditions, a set of common-sense assumptions about how energy is allowed to behave, assumptions built into much of our understanding of gravity. Phantom energy grows denser as the universe expands, which means the universe keeps making more of it out of nowhere, an ever-increasing amount of energy, filling an ever-increasing space. It is the kind of thing that, on paper, also lets you build wormholes and travel backward in time. Most physicists have long regarded a true phantom regime as almost certainly forbidden by nature, precisely because it leads to such absurdities, which is part of why the map's hint of a past phantom phase is so strange, and also part of why a future Big Rip is now seen as unlikely. Nature seems to dislike the phantom country, and the map suggests dark energy has already left it. Sit with the strangeness of that for a moment, because it is easy to say and hard to actually absorb. There may have been a version of the future, taken seriously by serious people, in which everything you have ever known was scheduled to be torn atom from atom at a specific and calculable moment. And the largest map ever made may have just quietly crossed that future off the list. Not through any action, not through any rescue, but simply by measuring the universe carefully enough to notice that the engine of destruction is idling down rather than winding up. It is a peculiar kind of good news, the kind that arrives with no fanfare in the form of a number that is a little higher than -1 instead of a little lower. A catastrophe that was never announced, averted by a measurement most people will never hear about. So, if these hints hold, the most violent ending, the one that rips galaxies and stars and atoms to shreds, becomes markedly less likely. The nightmare recedes. And I wish I could leave you there, with the comfort of a bullet dodged. But relief in cosmology has a way of arriving with a shadow attached, because the same weakening that saves us from the tearing does not simply hand us a gentle, open future. If the push keeps fading, and does not stop at fading, it opens a door to a completely different ending, one that physicists had quietly retired decades ago and had not seriously worried about since before most of us were born. A weakening dark energy takes the Big Rip off the table. What it puts back on the table is the possibility that the entire universe could fall back in on itself. Part 10. The ending that returns. The ending that the weakening puts back on the table is the oldest one we ever imagined, and for a long time it was the ending we assumed was ours. It is the Big Crunch, the universe collapsing back into a single point, and to understand why the map has revived it, you have to understand why we ever let it go. Before 1998, before anyone had measured dark energy, this was the great question that split cosmology in two. The universe was expanding. Everyone agreed on that. The only question was whether gravity would eventually win. If there were enough matter in the cosmos, its combined gravity would slow the expansion, stop it, and reverse it, pulling everything back together into a fiery collapse, a big crunch that mirrored the Big Bang. If there were too little matter, the universe would coast outward forever, thinning and cooling. For most of the 20th century, the Big Crunch was the romantic favourite, the idea of a universe that breathes out and then breathes back in, perhaps to be born again. Then, two things killed it. First, we measured the amount of matter, and there was not enough to reverse the expansion on its own. Second, and far more damning, we discovered in 1998 that the expansion was not slowing at all. It was accelerating. Dark energy was not just failing to reverse the expansion, it was flooring the accelerator. And so the Big Crunch was quietly shelved, filed away as a beautiful idea that the universe had declined to use. For 25 years, with dark energy pushing ever outward, a collapse seemed off the table for good. The weakening is what brings it back, because the Big Crunch only requires one thing that a fading dark energy might eventually provide. It requires the outward push to stop. If dark energy keeps weakening and does not level off, but continues to decline, then at some point the acceleration ends. And if it declines further still, past the point of doing nothing and into actively pulling inward, if the energy of empty space slips towards zero and then becomes negative, then the great outward push becomes a great inward pull. Gravity, patient and never defeated, only overruled, gets its grip back on the whole universe at once. Expansion slows, it stops. And then, for the first time since the Big Bang, everything begins to fall back together. I want you to see that reversal, because it is one of the strangest images in all of physics. Come and stand under the sky at the turning point, tens of billions of years from now, and watch the direction of the universe change. For your whole history, and the history of everyone before you, the distant galaxies have been running away, their light stretched toward red as the space between you widened. Now, slowly, that reverses. The reddening stops, and then, impossibly, it begins to swing the other way. The light of the distant galaxies shifts from red toward blue as they begin, ever so slowly, to fall back toward you. The night sky, which for 100 billion years had been emptying out and going dark, starts to fill again. Galaxies that had drifted apart begin to draw closer. Over enormous spans of time, the sky grows brighter and warmer and more crowded. The whole process of cosmic expansion running in reverse. The film of the universe playing backward. The galaxies rush together, then merge. Then the matter itself grows hotter and denser as everything is compressed. The cosmos heads back toward the fire it was born in, collapsing toward a single, unimaginably hot, dense point, a Big Crunch. The universe folding itself back into the seed it came from. Now, I have to be careful and honest here, because this is the most speculative ground in the whole story, and the discipline still applies. A hint, not a headline. The DESI map does not prove the universe will collapse. What it does is far more modest and far more unsettling than that. It removes the certainty that we were expanding forever. And once that certainty is gone, physicists have gone looking at the specific models that fit the data to see where they lead. Some of them are genuinely alarming. When researchers take the idea of a weakening, rolling dark energy field seriously and fit it to the DESI and supernova and background light data, certain versions strongly prefer a future in which the energy of space eventually turns negative and the universe recollapses. In one such analysis of a particular field model, the preference for an eventual collapse came out above 90%, and there is a twist that makes it land even harder. In several of these models, the collapse does not wait for a Google years. Unlike the heat death, which unfolds over timescales so long they lose all meaning, a recollapse driven by weakening dark energy could arrive in a matter of tens of billions of years. That is still far longer than the current age of the universe, and unfathomably far beyond any human concern. But on the scale of cosmic endings, it is almost around the corner. It would mean the universe is not a newborn with an eternity ahead of it, but something closer to middle-aged, with a definite and not infinitely distant end. The idea of a collapsing universe carries something the other endings do not, and it is worth naming, because it is why this scenario has always haunted the human imagination more than the others. A universe that collapses could, in principle, bounce. If everything falls back into a hot, dense point, some models suggest that point need not be the end at all. It could be a new beginning, a fresh Big Bang, a universe reborn from the ashes of the old one. This is the ancient dream of a cyclic cosmos, a universe that breathes out and breathes in forever, expansion and collapsion and expansion again, with no true beginning and no final end. Versions of this idea have been proposed seriously by respected physicists, some of them built precisely around a dark energy that weakens, turns negative, and drives a gentle collapse rather than a violent one. In those pictures, what the DESI map may be witnessing is not the approach of an ending, but the slow turn of a wheel that has turned many times before. The specific modern models are more sober than that, but no less startling. When researchers take the weakening seen in the data and follow it forward with a particular kind of dark energy field, one whose energy can slide past zero and become negative, several of those models predict that the universe reaches a turning point and begins to collapse. And the timeline that falls out of some of them is the truly arresting part. Rather than the endless spans of the heat death, these collapses can arrive within a few tens of billions of years. To put that in perspective, the universe is currently a little under 14 billion years old. Some of these models suggest the whole story, beginning to end, might run only 2 or 3 times that long. It would mean we are not near the dawn of an eternal cosmos. It would mean we are somewhere in the long afternoon of a universe with a real, countable number of years left. I cannot stress enough that this is the far edge of speculation, built on a hint that has not yet cleared the bar of discovery, stacked on top of a specific choice of model. But that is exactly what makes this moment so remarkable. A single tilt in a single map has made physicists dust off the collapse, take the cyclic universe seriously again, and calculate, with real equations, how many billions of years the cosmos might have left. Ideas that were shelved as beautiful impossibilities are back in the working notebooks. So look at what the map has done to our 3 endings. It has weakened the case for the slow, cold heat death. It has pushed away the violent tearing of the Big Rip, and it has reached into the past, pulled out the collapse we thought we had ruled out forever, and set it back on the table, possibly as the nearest ending of them all. This is why a quiet map frightened the people who made it. It did not just change one number, it reshuffled the fate of everything and left the deck face down. But before we let ourselves fall too far into any of these endings, intellectual honesty demands that we turn and face the strongest argument against the whole thing. Because there is a serious possibility that dark energy is not weakening at all and that we are being fooled. Part 11. Or maybe nothing at all. There is a real chance that none of this is happening, and honesty requires that we take that chance seriously. A hint, not a headline. I told you to keep that phrase in your pocket, and this is the part of the story where we take it back out and let it do its real work. The most respectable objection does not come from cranks. It comes from careful physicists who think we may have been misreading the universe for 25 years, and not in the way the map suggests. Their argument turns on a fact we tend to gloss over. When cosmologists calculate the expansion of the universe, they usually assume it is smooth, the same density everywhere. But the real universe is not smooth. It is lumpy. Matter is gathered into galaxies and clusters and long, bright filaments, and between those filaments lie enormous, nearly empty regions where there is almost nothing at all. According to one alternative model, called the timescape picture, that lumpiness matters more than we admit. Time and distance behave slightly differently inside a dense filament than inside an empty void. And if you account for that unevenness properly, some researchers argue part of what we have been calling acceleration might be an artifact of assuming a smoothness the universe does not actually have. In that view, Dark energy might be less real or even not real, and the tilt in the map could be a symptom of using the wrong idealized model rather than a true change in the pressure of space. What makes the timescape idea worth taking seriously, rather than dismissing, is that it does not require any new physics at all. It does not invent a mysterious substance, or a new field, or a correction to gravity. It only asks that we stop pretending the universe is smooth, when we can plainly see that it is not. Between the bright filaments of galaxies lie enormous, nearly empty regions, and light that crosses those emptier regions has spent most of its journey in places where time and space behave a little differently than in the crowded parts. The people advancing this view argue that when you add all of that up honestly, some of the apparent acceleration is a side effect of our own convenient simplification. Most cosmologists are not convinced, and the standard picture with dark energy still fits the full range of evidence more comfortably. But the fact that a serious, physics-free alternative can even stay in the conversation tells you how much room for doubt still exists. We are debating not just the value of a number, but whether the number is measuring what we think it is. There is a second, more down-to-earth worry, and it lives inside the exploding stars. Remember that a great deal of this rests on those Type 1a supernovae, the ones we treat as having nearly identical true brightness. But what if they are not quite as identical as we thought? What if a supernova that exploded 10 billion years ago in a young galaxy made of different stuff is subtly brighter or dimmer than one that explodes nearby today? If the brightness of these markers drifts even slightly with the age or chemistry of their surroundings, then our distance measurements drift too, and that drift could masquerade as evolving dark energy without a single new law of physics. This is not a wild idea. It is one of the leading things the skeptics point to, and it is genuinely hard to rule out. And then there is the plainest objection of all, which is simply the statistics. 3 sigma, or even 4, is not proof. It is the level at which the history of physics is littered with tantalizing signals that later evaporated, particles that seemed to appear and then vanished with more data, anomalies that turned out to be a miscalibrated instrument, or an unlucky run of noise. The strength of the DESI result also shifts depending on which supernova set you fold in, and even on some of the technical choices in the analysis, and a result that moves around like that has not yet earned the word certain. It has earned attention, and it has earned more looking. That is all, and that is a lot, but it is not everything. I even want to be fair to the wilder voices at the edges, the ones who hear weakening dark energy and reach for a breathing, cyclic universe, or claim it as proof that reality is a simulation quietly running low on resources. The right response to those is not mockery. It is the same discipline we have used all along. Those ideas are not what the data shows. The data shows a small, stubborn preference for a changing push, measured with an ancient ruler that has not yet cleared the bar we set for belief. Everything beyond that, in either direction, toward collapse or toward a cosmic rebirth, is a story we are telling around the edges of a number. A beautiful story, maybe even a true one, but a hint, not a headline. History gives us every reason to stay humble here, because physics is littered with thrilling signals that arrived at 3 or 4 sigma and then quietly died. Not long ago, an experiment in Europe seemed to show particles called neutrinos traveling faster than light, a result that would have overturned Einstein. Physicists were cautious. The world was electrified, and in the end, the cause turned out to be a loose cable in the apparatus. Around the same time, a telescope at the South Pole announced it had seen the fingerprint of gravitational waves from the birth of the universe, a genuinely historic claim, and for a few months it looked like a Nobel Prize. Then a closer look showed the signal was mostly dust in our own galaxy, and it evaporated. A few years after that, both big detectors at the Great Collider near Geneva saw hints of a new particle at the same mass, Exactly the kind of coincidence that gets physicists to book flights to conferences. More data came in, and it melted away into nothing. Each of these was more than a hint. None of them survived. That is the company the dark energy result keeps right now, and the scientists know it. There is also a subtler statistical trap worth naming, sometimes called the look elsewhere effect. If you allow yourself enough ways to slice the data, enough models to try, enough parameters to let float, you will eventually find something that looks significant purely by chance, the way a long enough run of coin flips will eventually throw a surprising streak. Cosmologists work hard to account for this, but it is another reason to hold the result loosely. The evolving dark energy signal is genuinely interesting, partly because it did not fade with more data, which is not how most flukes behave. But not fading is not the same as being proven, and everyone serious about this is careful to keep those two things apart. Then there is the deepest skeptical possibility of all, the one raised by the timescape idea, which says the problem is not our data, but our entire framework. If we have been oversimplifying the lumpy universe into a smooth one for 100 years, then dark energy, evolving or not, might be partly a shadow cast by our own assumptions. That would be the most humbling outcome imaginable. Not that we discovered dark energy is changing, but that we finally noticed we had been misreading the geometry of the cosmos all along. I find something quietly admirable in all of this caution, and I think it is worth defending, because from the outside it can look like scientists hedging or refusing to commit. It is the opposite. The willingness to say we are not yet sure, in the face of a result you would love to be true, is the whole engine of how we come to know anything real. A field that let itself believe every exciting 3 sigma hint would be a field constantly lurching from one overturned certainty to the next, and it would never build anything that lasts. The reason we can trust the parts of physics that are settled is precisely that the community is this stubborn about the parts that are not. The doubt is not weakness. It is the price of eventually being right, and it is paid gladly by people who would genuinely love to see the universe turn out to be strange. The honest position, then, is a strange and almost uncomfortable one to sit in. We have a serious result from a serious instrument that genuinely might rewrite the fate of the universe, and we are not yet allowed to believe it. Both of those things are true at once, and the maturity of modern cosmology is that it can hold them both without flinching. The wonder is real. So is the doubt. And what makes this moment so unusual is that, for once, we will not have to wonder for very long. The verdict is already on its way. Part 12. The ending nobody has written yet. We are living in the short window between a question and its answer, and I do not think we appreciate how rare that is. For almost all of human history, the fate of the universe was pure speculation, a matter for philosophers and poets who had no way to ever know. And then, for 25 years, we thought we had it settled. Dark energy was constant, the expansion would run away forever, and the universe would end in cold and dark. It was written. We moved on. What the largest map ever made has done is not simply to propose a new ending. It is to take the pen that we thought had finished the sentence and lift it back off the page. The ending has come unwritten. And for the first time in decades, if you ask a cosmologist how the universe ends, the most honest answer is the one they have not been able to give in a generation. We do not know. The reason we will not be stuck in that uncertainty forever is that an entire fleet of new eyes is opening on the sky. DESI itself is still running, still adding galaxies to the map, and its full survey will sharpen the very measurement we have been talking about. A space telescope called Euclid is already mapping billions of galaxies to trace the same expansion history from orbit. A new observatory in Chile, the Vera Rubin Observatory, is beginning a 10-year survey that will watch the sky change night after night and catch supernovae by the millions. And a space telescope named Roman will measure cosmic distances with a precision we have never had. Each of these looks at dark energy in a different way, with different instruments and different weaknesses. Within a handful of years, they will either drive this hint up past the bar and into the territory of discovery, or they will watch it dissolve back into the flat line it strayed from. Either way, some of the people listening to this will very likely live to hear the answer. That almost never happens with a question this size. There is a temptation, when facing questions this large, to feel small and to leave it there, as if the size of the cosmos were a rebuke. I want to push gently against that. Yes, the timescales we have been discussing are so long that a human life does not register against them, and none of these endings, cold or torn or collapsing, will ever touch anyone you will ever know. But the ability to know about them at all is not nothing. It may be the rarest thing in the universe. As far as we can tell, the cosmos spent most of its history with no one in it to ask how it would end. And then, on at least one small world, matter arranged itself into minds that could look up, measure the light of galaxies 11 billion years gone, and reason their way toward the fate of everything. The universe grew a way to wonder about itself. That the answer is still uncertain does not diminish that. If anything, it makes the wondering feel less like a lecture and more like a living question we get to hold. I keep returning to where this all started, on that mountaintop in Arizona, with 5,000 small robotic arms swinging in the dark. There is something almost unbearably human about it. We are the 5%. We are the thin, bright foam of ordinary matter floating on an ocean of two things we cannot name. We are made of the minority ingredient, living for a flicker of time on one small world, around one ordinary star. And from that position of almost total insignificance, we built a machine that could look back across 11 billion years, read a ruler made of sound from the dawn of the cosmos, and catch the faint suggestion that the emptiness of space is quietly changing its mind about how everything ends. There is no reason a species like us should be able to do that. And yet here we are, doing it. I called dark energy the one fixed thing. That was the promise we made to ourselves when we could not explain it. We could not say what it was, or why it had the value it did, or where it came from, so we told ourselves that at least it would never change. It was the steady flaw under a restless universe, the single, unmoving certainty we could build a future on. And the map has gently, patiently suggested that the one fixed thing was never fixed at all. That the flaw has been tilting the whole time, so slowly that we only just noticed. There may be nothing in this universe that holds perfectly still. Not the stars, not the galaxies, not the atoms in your body, and perhaps not even the emptiness between them. I find that I cannot decide whether that is a frightening thought or a comforting one, and I have come to think that it is both, and that it is supposed to be both. It means the ending is uncertain, and uncertainty about the end of everything can feel like standing at the edge of something with no bottom. But it also means the story is not over, and was never as closed as we believed. A universe whose fate is still being written is a universe that is still, in some sense, alive with possibility, right down to its final chapter. The cold dark, the great tearing, the long fall back into fire, all three are still on the table, and the map has only told us that the question is open, not which answer is coming. It is worth being specific about how the answer will actually arrive, because it is not a matter of waiting for a single dramatic announcement. It will come the way real cosmology always comes, as a slow tightening of the numbers. The same instrument in Arizona is still on the sky most clear nights, adding galaxies to its map, and each additional year sharpens the very curve we have been talking about. The Space Telescope, mapping billions of galaxies from orbit, will report its own reading of the expansion history, using gravitational lensing and the shapes of distant galaxies rather than sound waves, an entirely separate method that can either agree or disagree. The new observatory in Chile will watch the whole southern sky repeat, night after night, catching supernovae in numbers that will dwarf every catalogue we now argue over. And a little later, another space telescope will measure cosmic distances with a precision we have never had. If 3 or 4 independent methods, with different instruments and different weaknesses, all keep landing on a dark energy that changes, the hint will harden into a discovery, and the word will finally be earned. If they scatter, the tilt will dissolve. Either way, we are not talking about centuries. We are talking about years. Think about what it would mean to actually cross that threshold. If evolving dark energy reaches the level physics demands, before it will use the word discovery, it would be the first genuinely new ingredient added to our picture of the universe in a generation, and it would retire the simple cosmological constant that has anchored the field since before many of us were born. It would mean the standard model of cosmology, the one in every textbook, describes a special case rather than the truth. And it would mean that the question of how the universe ends is not a fixed fact to be looked up, but a live problem, being decided right now, in our lifetime, by machines we built and people who are alive today. There is a thought I keep coming back to, and I want to leave it with you, because it reframes the whole strange situation. For every generation of humans before ours, the fate of the universe was simply unknowable, a thing you could wonder about but never test. And for every generation after ours, if the answer comes as quickly as it might, it will be settled, a fact learned in school, like the distance to the sun. We happen to be alive in the narrow seam between those two conditions. We are the first people with instruments powerful enough to ask the question seriously, and possibly the last people for whom the answer is still a genuine mystery. That is an extraordinarily specific window to be born into, and none of us chose it. We simply arrived at the exact moment when the largest question there is stopped being philosophy and started being data. So the next time you find yourself awake in the dark, and the whole weight of the universe feels settled and finished and indifferent, I want you to remember a quiet map drawn by robotic arms in the desert, and the small tilt in it that reopened the largest question there is. Nothing about how this ends is decided yet. The universe is still making up its mind, and somehow, against all odds, we are here to watch it think.